Okay, good afternoon, everyone, and welcome to our TEWI-Kolloquium. It is a pleasure to welcome Leonardo Galteri from University of Florence here with us. He did his PhD study in Florence, and also he co-founded a startup called Small Pixels. So he has two hats on university and on the startup. And actually, we met him not in Europe, but in Denver at ACM Mile High Video conference, the first edition, where they also presented something. And then also we came into the discussion, and that's why we invited him here to the University of Klagenfurt to give a talk. And the title of the talk you can see on the screen is Advances in Visual Quality Restoration with Generative Adversarial Networks. Very interesting title, and what's behind that, let's see what Leonardo has to say here. So welcome, and looking forward to a very good talk. Thank you very much.
First of all, I want to thank Professor Christian Timmerer and Ekrem Setinkaya for inviting me. This is a very good opportunity to explain to you my research, what I'm doing, I've been doing so far for my university. So the title is Advances in Visual Quality Restoration with the Generative Adversarial Networks. First of all, one might ask, well, why? Why we want to restore, and what are we restoring? Okay, here we are talking about images and videos. So visual quality is about images and, more important, videos. We use deep learning. We use some kind of artificial intelligence to restore the quality of the images and the video. Let me show you an example. Yeah, you might know what is this. This is about Game of Thrones, a TV series that went viral like a few years ago. This was an episode from the last season. Fans were almost disappointed how the things were going, and this particular episode was one of the last. It was the climax of the entire series, and not only for the specific season. And for some reason, the directors choose to make this episode very dark. During the night, there was so few lights, and the people could not see very good what was happening. But this was also a problem because the quality of the video was very low. This is actually a frame that has been photographed by someone, and this effect of posterization blockiness was the real issue. So many people was complaining about the quality of the video, and it was not good. Yeah, this happened because of the compression of the video. So compression was the reason the quality was that bad. Okay, but why? Why should HBO compress so much this video? Well, the reason is always the same. It's money, the problem, because the more you have to send the data to all the user all over the world, the more you have to spend. And so if you want to save money, you have to send less data, and for that reason you have to compress the videos. We have done some rough estimate of how much this can cost to a company, how much cost the transmission of a single episode. We do that for Stranger Things, a very popular TV series. We estimated that the first episode of season 2 had something like 15 million viewers, and we estimate that each stream would cost something like $0.020 per gigabyte. And then we estimate something like 1 million, slightly more than $1 million of dollars for airing the single episode of this series. You know that if you multiply this single cost for the entire season, for all the season of a TV series, and then by all the TV series that a content producer is having, yeah, you know that the costs begin to rise, and they need to do something about it. So compression is a way to do it. How do we fix this problem? Okay, one thing is to work on the encoder side. That is, you may want to use encoders. They are smarter to compress as much as possible the data and still have high quality in output. Or we did something like this to have some aspects of the videos high quality. Like at the first, when I entered my laboratory, we was working on the encoder part, and we choose a feature of the old H.264 encoder, where you could choose to keep high quality a single part of an image and lower the quality of the other parts of the video. I mean the background. You didn't need to see the background high quality, and you lower the quality as much as you want. We did some very simple algorithm. We take some feature like saliency. We take some other feature like objectness. We put all this together. We build some kind of saliency map that was specific for objects, and we use that this map to drive the compressor, in this case X.264, to maintain high quality the objects and compress very much everything else. Yeah, this could work. This could be a solution, but you can use for some constrained situation, like video surveillance. Yeah, you have, I don't know, some pedestrians you have to track. Okay, you can monitor this pedestrian high quality, and you maintain the background as compressed as you want, as much as you want. You don't need it. But when we are talking about entertainment, you don't want to see something like this, because you will have another long night effect as before, meaning that posterization, blockiness, ringing everywhere is not very pleasant for the users. So, is there another way to fix the problem of compression, heavy compression? Well, this is what we have done since that moment. We had another idea. We didn't work anymore on the encoder. We left the encoder intact, the same as before. You can use, you can think of an encoder as a black box. You can use whatever algorithm you want to compress the image. In our idea, the fixing of the compression is on the other side, on the receiver side. So we want to use deep neural networks, in particular convolutional neural networks, to take these compressed frames, compressed images, and transform them into something that is more pleasant for human eye. So the procedure is something like this. You have on transmitter side the high quality frame, okay? You compress it, or here is like JPEG-like, but again, don't you worry about the encoder, you can use whatever you want. Then you transmit to someone, and then you use this deep convolutional neural network to restore his quality, to have your quality back, your missing details, to have something you would like to see. So we start formalizing a little bit the problem. Here we are talking about compressed images. So given an uncompressed frame HIQ and a compression algorithm, let's say C, our model is wants to learn a function that's some kind of makes some kind of inversion of this process. So C minus 1, and we want to learn a set of parameters, like the parameters are the one that are learned inside the neural network. So we are talking about neural networks. We use a neural network to restore images, and that's how we do in particular. Probably many of you might know what neural networks are, and might know that there's a specific architecture called residual network that is very common for classification. It's very effective, I would say. We use this kind of model to reconstruct our images. We've used the idea of a residual block and constructing the network with this residual block. We build the entire network to be capable to take in inputs a single image of whatever dimension you want, and give in output an image with the same dimension and the same channels. So you may think this kind of network as a series of filters, and each filter has a function, a certain function. He's trained to do something, and the whole network is trained to restore the quality. We did some minor adjustment for this network to make it work, and we trained initially with a kind of error, a kind of loss called the mean square error. That is, there was kind of supervision between the restored image and the one uncompressed. We calculate the error between these two, pixel by pixel error between these two images, and the error was then back propagated in the network to learn the optimal parameter. We did this, and this is what we obtained. It was 2017. This was the start of our journey into this field. Okay, let's check these three images. The leftmost is the compressed one. Here we use the standard JPEG compressor. You can see there's a lot of blocks. The quality is very poor. The original one is the rightmost image, how it should be a high quality image. The reconstruction of the model I was telling before is the central one. You can see that in this image, most of the blocks and ringing artifacts are gone, but there's something missing here, like the details. Training a network with just MSE, mean square error, leads to results that are okay, but nothing more than that, because that kind of training doesn't lead to having high frequency details that are that are responsible of the real quality of the images. So what we do is to introduce a new technology, Generative Adversarial Networks, that helped us to bring back those details that were missing in the reconstructions. So this framework is very common now. Back then, it was not so so famous, but let's say that many people since then have been using this particular fashion to train their network. GANs is shorthand for Generative Adversarial Network, are useful to make photorealistic images. Probably many of you would have seen something like faces that really don't exist, and those faces are created by GANs, basically. So you have noise, you use a framework like this, and you can generate an infinite number of faces that really don't exist. Here, the principle is very similar, but in this case, we use GANs to restore the quality of the images. Here is a basic way to work. You have two networks, not just one as before, but two networks, a generator and a discriminator. The generator is the same as before, a fully convolutional network that takes in input the image and outputs another image that has the same dimension as the input one. And then there is a discriminator. The discriminator is mostly like a classifier network. So as the other network, you may know that classify images and tell, I don't know, like this is a dog, this is a cat, and so on. This particular network has the same architecture. You give in input an image, and he gives in output a prediction. The prediction is real or fake. But what does it mean, real or fake? We assume that we have a high-quality data set, and we call real those images. On the other hand, the restored images are called fake because they really don't exist. They are reconstruction of the low-quality images. And this is how it works. Once you have generated your fake image, you ask the discriminator whether, in its opinion, is it real or fake. And this decision guides the network to be trained in a way to drive the reconstruction to be more photorealistic. And this actually works very well. We did some adjustment to discriminator because we were experiencing some mosquito noise in the reconstruction. So what we did is to split the patches of the image in input to the discriminator in smaller patches, concatenating them with the input, and then making the discriminator do the decision. And basically, this reduced pretty much the mosquito noise in the reconstruction. For anything else, the discriminator is just a simple classifier network. But what is very important for the training of again is the generator loss, because you always find that something like this always need at least two components to work. The loss is composed, the loss that you need to train this kind of networks is composed by two components. One, we call that content loss, and the other one is the adversarial loss. The content loss here, it's LP, is roughly related to content, meaning that you can use the supervision of pixel-wise, like we did before, meaning that you calculate the error between the original uncompressed image and your reconstruction pixel by pixel, and this works. Or you can do, like we did in this case, using a perceptual loss, meaning that you take a pre-trained network, like VGG19, pretty common network to do some kind of classification. You give an input the original image and the reconstructed one. You take the feature in output at some point in out of the convolutional layer, and then you take these two feature maps, and then you calculate the mean square error between the two. This works very good, and I like more this solution than the standard MSC between pixels, but these are detail. This is the perceptual loss and helps the reconstruction to be good, to be very close to the original to the original one, making the reconstruction to be very close to the original one. And then you have the adversarial loss. The adversarial loss is the one that comes from the discriminator, and actually it measures how good is the generator in fooling the discriminator, meaning that if you generate high quality reconstruction, you will fool the discriminator, meaning that this error will be low, and the backpropagation of this error will lead to few minor adjustment to the weights of the network. On the other hand, if this loss, this error is high, it would mean that you're not fooling the discriminator, so the error you backpropagate will be huge, and the adjustment on the weights will be many more. So this is how to train the network from the point of view of losses. So this is about the subpatch discriminator, the adjustment we did for removing the mosquito noise. You can see it very well, but trust me, there are many strange artifacts all around the objects in background, noise that you don't want to have. Using our discriminator with subpatch helped us in generating higher quality reconstructions. Okay, and this takes us to another problem. I've been talking about reconstructing images that have been compressed with JPEG. The problem is that you can have, let's say, a JPEG on your phone or your computer that you want to restore, but you don't know what is quality factor. You don't know which quality factor has been used to compress that image. This could be a problem, because if you train a network to restore images that have been compressed with quality factor 20, and then you try to restore another image that have been compressed with the QF, let's say 60, you will get very bad results. So what you have to do is or training the network with many quality factor altogether, but this is not the optimal solution, because the network we won't be able to do a proper job all the time. Or you could train a CNN regressor, meaning that you could try to predict the quality of the image before feed the image in one particular generator. So you train this QF predictor, and then you feed the image in the right position so that its reconstruction would be optimal. To our surprise, this prediction of the quality was very effective, meaning that we use a very simple classifier network to guess the QF of the images, and we used like VGG 16 pre-trained. We fine-tuned that network, and it led to very good results. Here you can see the confusion matrix on the right, and most of the time we guessed right the QF, and when we didn't, the error was not so high. The predicted QF was very close to the one to the target one. So, meaning that this prediction module of the quality factor was smart enough to drive the quality of to drive the reconstruction of the image to the right, to the correct, the optimal generator to do his job. Okay, we'll talk about the method, the approach, how it works, but let's see the outputs. Let's see the results. Here you can see our results from our journal TMM19. We have on the leftmost column the input JPEG compressed image. I think this is like QF20, so very bad quality. The second result is an approach. The second column is an approach that is based on MSE loss reconstruction. You can see it's fine, but the results are very blurry. It's not really satisfying. In the third column, our result. You can see that the reconstruction bring back to life many high frequency details that are missing in the compression, and from the realism point of view, the reconstructions are quite similar to the original ones. Yeah, you wouldn't have the same exact details. I mean, the images are not equal, but you get the impression they are very close. And this is enough for our eyes to be satisfied. So this is something I would like to see in a reconstruction for entertainment purpose. And the fact that the details are not exactly the same as the original content wouldn't be so much a problem. To be fair, we asked people to evaluate our reconstruction, and they told us we were right, basically. Each time we make them see our reconstruction with GANs, they were satisfied. They give high scores to those images, and then we made them see SSIM loss reconstructed image. SSIM is much similar to MSE. Basically, you can think they are pretty much the same. So blurry reconstruction, they didn't like it that much. So even people recognized that our reconstruction with GANs were better. Then we did other kind of experiment to assess the quality of our reconstruction. That means we use some other metric to ensure our work was good. We use an object detector, let's say faster RCNN, to compute the mean average precision on a detection dataset, meaning that if those images have been restored in the correct way, the detector would have scored high values of mean average precision. That's what happened actually for highly compressed images, and we took another Q. that is this improvement in MAP for again reconstructed images was given by certain classes. You can see in the table here, dog, cat, sheep, cow. These are not random classes. These are specific classes that are deformable objects and furry. That means they are heavily textured. If you use GAN to restore heavily compressed image, it's better because during the compression process you lose most of the textures, and GANs helps you to restore this kind of high frequency details that compose the texture. In this case, if you try to use the detector on this image, these reconstructed images that contains the texture, you are able to detect correctly the classes. So if a dog, if you compress an image where there is a dog and try to use the detector over it, you might get a misclassification. I don't know. It could be classified as a cat, as a cow, as a chair. We don't know. But if you reconstruct with our GAN method, it will bring back the high frequency details that compose the texture of a dog. And if you run the detector over the reconstructed image, you will get the right classification. This was one of our best results for this kind of paper. But let's move forward, because we'll talk about evaluation even later in more detail. At some point, we did some kind of evaluations about the speed of those networks, and we say, okay, these networks are capable to reconstruct the compressed image very well, but yeah, they don't go so fast as we expected. So what we did is to make all the things quicker. Those was the years where when MobileNet was published. When MobileNet, it's a classifier network as much as the one I've told before, and this particular network works even faster. Works very fast, and we use the concept of this MobileNet to build a new network that could run even faster than that. In particular, mobile network uses stepwise separable convolution and inverted residual blocks to obtain the same performance as a standard convolutional networks, but in less time, basically. So, if you remember the architecture I've told you before, we just took those residual blocks we've been using before, and we replaced them with these new inverted residual blocks. The operation was super simple, and we did some minor tweaks to improve the results slightly more, and this is what we obtained. On the right, there's the raw image, meaning that this is taken from a video, actually. And we used the X2C4 to compress those video. On the right, there is the raw uncompressed image, no compression here. And the left part of the slide, you can see the reconstruction. This is our original work, where we had the regular convolutional blocks, residual convolutional blocks. You can see the reconstruction is good. It's quite similar to the original, but it runs at 4 FPS on Titan XP GPU, meaning that is not real time at all. Replacing those residual blocks with MobileNet ones and using very few of them resulted in something like this. Okay, this kind of choice was very fast, run in at real time, like 42 FPS in the same GPU, but you can see the results are not very pleasant, because in this case we had very few convolutional layers and were not able to properly elaborate the signal. So this was our in the middle solution. We used a few more of these inverted blocks that leads to a solution that ran in 20 FPS on the same GPU, and the reconstruction was very similar to our original solution, but it ran 5 times faster. And this is a comparison with another technique that involves learning the compression, and trying to reconstruct it. You can see that compared to our method, all the details have been eliminated. You can see the shape has changed. The solution is not really pleasant. Differently from this approach, our approach not only is acceptable for any of you, for the users, because it retains most of the details, but in this case runs almost real time, let's say 20 FPS in this particular GPU. And as far as I'm concerned, I will tell you some details about the numbers. We have measured those videos, the reconstructed videos, for any solution we tried, and we have seen that basically our in the middle solution here called fast leads to results that are really comparable to the original solution, TMM19, and the matrix shows that there was not a big difference between the two of them. But as I said before, it ran 5 times faster, and it had like 3 times less parameter than the original model. So if you want to go faster, you have to make some adjustment to the architecture, and you may be fine. MobileNet is a way to do it. I guess now in 2022 there are other ways to improve the architecture and make things even faster. But there is another thing we could talk about in order to make things faster. That is working with highly specialized content. In this case, faces are one of the most studied arguments for all the computer vision world. And faces are very structured. You have the eyes always in the same position, nose always in the same position, roughly the mouth even. So the distribution of these faces is very narrow with respect to other kind of content you may use. So if you want to go fast, one way to do it is using very specialized content. That's because you can reduce very much the size of your architecture, of your neural network, and go as fast as you want. Here you can see what we did. This work was presented at ACM Multimedia 19, and it has been awarded as best demo. we take the problem of compression to its extreme, meaning that we had very small faces, let's say 128 by 128, very, very, very small. And we wanted to upscale those images to 4 times its their dimension, meaning that we want to bring that to 512 by 512. And those small images were even heavily compressed, like 30 CRF with the H.264 compressor. So it was a very, very, very discouraging context. But here's what we did. You can see there is a huge difference between the input images and the output. Despite of the compression, despite of the heavily downsampled process, we were able to reconstruct those images because of this narrow, simple distribution that are faces. And trust me, we use a very, very, very lightweight CNN. And again, we trained was able to do that. You can see even some example in more detail. Here is what the network would take in input, and this is the output. Again, another one, heavily compressed, very downsampled. With few layers, we have been capable to do this. And this is another example. This is a video. This is a colleague of mine. The video has been compressed with the same parameter as before. This is the input video, and then this is its reconstruction. We were able to run this network on an iPhone X, meaning that a phone that was released like 4 years ago, or 3, I don't remember, was able to run a lightweight network real time. So this is why they appreciate our contribution, because it was fast enough to run on the mobile device and able to bring back many, many details to a very compressed video in input. So we're going forward, and we move on, studying on phases again. And do you remember at the beginning of the talk, I've talked about semantic compression, that it could work, but was not optimal. And we asked ourselves, but if we compress in a semantic way the video and then we reconstruct it, would be a viable solution? The answer is yes, basically. So we devised a pipeline like this. Since we are talking about faces, we use some video conferencing setup. So here in this video, all the people were talking about in front of a video camera. Just I am doing it in this moment, and we use this context to join the benefits of semantic coding and GAN restoration. In the transmitter side, we took the original frame and compressed. Then we used a face parsing algorithm to try to understand where the face is located inside the frame. Then we applied a semantic coding in order to preserve more the details of the face of the person and compress anything else. On the receiver side, we get this video that is adaptive compressed, and we take this weirdly compressed video to restore with GANs. This is actually this was actually very effective because not only you preserved many more details for coming from the face of the people, but even you were able to restore partially the background. That is all the blockiness, the ringing, all the artifacts you would have with the standard semantic coding would be eliminated by the GAN restoration, and this was a very pleasant effect to who observed our restored video. For the semantic segmentation part, we used an algorithm that someone else designed called BizaNet. We could have used any algorithm. That's not a problem. There are many of them, and the point is we need just to do some face parsing and understand where the face is, where the eyes is, where the nose is, in order to tell the encoder which parts are important, where to allocate more bits and where to allocate less. In other words, we need to establish a way to separate the foreground to the background. We did something else in this work because we knew which one was the background and which one was the foreground. So we trained our network, our restoration network, in order to treat differently the pixel belonging to the foreground and those pixels belonging to the background. We used two different perceptual losses. The one for the background was a standard, the one I've explaining before, VGG loss, meaning that we take the pre-trained VGG and we use the feature to calculate the distance. But since the foreground is basically a face, we have used a VGG face as the pre-trained RAN network, because VGG face has been trained on faces, and that is better to reconstruct faces because the feature that has been learned with VGG faces are more close to the one we are dealing with in this particular case. So by joining these two contribution, our final reconstruction was better than the original solution. These are some results. Here we obtained like 30% of improvement. Okay, here the orange line is the baseline, the one where you don't reconstruct, the GANs does not exist, and you don't reconstruct the image. The blue line instead is the one that where we are using the restoration. The semantic compression happens if we are considering we are not considering the coefficient on the x-axis. Like at the 0, there is no semantic compression, and the more we move right to the right in this x-axis, we are allocating 5% of bits more in the foreground, and so on. So the more we move toward the left part of this graph, the more we are compressing the background. So here we can see two different results. LPIPs bring, for an LPIPs perspective, we obtain 30% of improvement, and the BRISQ 55 improvement. They are huge improvement if you consider that here we are doing we are dealing with very highly compressed videos, and we want to obtain pleasant reconstruction. And just for letting you see what we did, this is what you all have without using any of the technique. This is plain H.265 compression. So you can see there are a lot of artifacts all around the image. You can see the face is also very compressed. Many details are missing. Other things are distorted. This is not what you want to have. Then we used the saliency, meaning we have here we are using semantic compression. So here we are allocating more bits in the foreground to the face and partially the body of the person, and you can see that the background is even more compressed with lesser and lesser details. This is an okay solution, meaning that we still have more feature for the face, and it's good, but overall the quality of the video is not on point. And this is after we use the reconstruction. So we are allocating bits on the face, so in the transmission much details of the face are not lost, and we are reconstructing on receiver side, so overall there are no artifacts, blocking artifacts, ringing artifacts, and so on. So this is a good compromise. Joining these two techniques leads to a pleasant and useful results for us to watch. Then we are moving forward to the last part of this talk. This is our last paper, last work for the world of reconstruction GANs, and it was in 2021. This was selected as the best paper award as in ICM Multimedia Asia, and we are trying to understand the problem of evaluating the images. We are talking about quality, how to evaluate the quality of image. The problem here is that GANs are very hard to evaluate. That's because if you use standard metrics like PSNR, SSIM, and so on, you wouldn't get very good results. Yeah, at first, when we tried to evaluate our results, we were, oh, come on, how is it possible that PSNR is even lower than the compressed image? That is nonsense. It's not possible. Actually, it did happen because of the details that GANs are bringing back to life and are not the real details. They're more like hallucination. So you use some signal-based metrics that evaluates the quality pixel by pixel. You wouldn't find many matches between them, and so you don't get a high score for those measures. So we've been interrogating how could we do for correctly evaluate this kind of reconstructed images, since PSNR doesn't work. Starting from our first work on GANs, where we have seen that detection could be considered a good proxy for evaluating GANs, we take this problem to a higher level. So we use language to evaluate the quality of images. Let's look at these three images. We have an image of a dog compressed with JPEG compressor, and if we try to use a captioning algorithm on this image, we obtain something like this: a statue of a woman wearing a Christmas tie. This is hilarious because this is not clearly a statue of a woman, but it's a dog. The correct caption is the rightmost, a brown and white dog wearing a red tie. If you try to reconstruct the JPEG image with one of our solution, you obtain a high quality image, and if you try to run the captioning algorithm on this reconstructed image, you will obtain a phrase like this: a brown and white dog wearing a tie. That is very, very close to the ground truth one. So, meaning that language could be used to evaluate the quality of our image. This is how we do. The algorithm is really simple. Anyone can implement this kind of solution in minutes, I would say. This is how a captioning algorithm is working. It's a simple network. You extract some visual features from this, the image, use these visual features, these objects you're extracting from the image, to elaborate them in a language model. The language model generates a series of words, white and brown, etc., etc. Then you compare the predicted caption with the ground truth caption, so that you obtain a certain score for depending on the metrics you are using to evaluate the generated sentence. And this metric could be a good proxy for the quality evaluation of our of the image. You can do it even if you don't have a ground truth caption for an image. Let's say you have a data set without anybody that have given the caption for those images. There is no problem, because you can use the very same language model to generate ground truth caption, and then calculating the score between the caption of the compressed or the constructed image with one that you generate with the ground truth, and this could be a good option as well. So a little bit of result. We can see that this kind of approach it correlates with mean opinion score. That could be used in some situation, in some specific context to evaluate the image. The actual method we devised is not really ready yet, but we're getting there, because we believe that if we had better language metrics, better language models, this way to evaluate the quality will improve in time. We have seen something like this just by changing the language model of our pipeline, so that we tried two different methods, one with a standard convolutional model, and another one with transformers. And we have seen that if we use a better captioning, a captioner that performs better, the quality is evaluated better. So the more the captioner works better in generally speaking, the more this particular method to evaluate the quality of image works better. Here, okay, this is what happens from a visual point of view when you are trying to evaluate the image with the captioners, with language. In the left part of the slide, you can see there is a highly compressed image. If you try to run a captioner over there, you can see that the generated caption is a couple of people sitting next to a Christmas tree. Completely wrong. And this happens because you have some kind of bad detection, like white tree, blue wall, white floor. Yeah, the compression is distorting this feature and make the captioner think these things are present inside the image. But if you do the restoration part, if you try to restore the the compressed image with a GAN, you will see that those bad detection turn in good detection, because the blue wall became blue water, the white floor became white wave, and then something appears that was not present before, like white surfboard. So if you try to run the detector and the captioner on the reconstructed images, in this particular case, you will obtain a man riding a wave on the surfboard in the ocean. It's not a complete complete caption, but yeah, I think it can work. And if you compare this caption with a ground truth one, you will obtain a very high score. So this is how we might do to evaluate our images. So we are at the end of this talk. Just some word about what's next. Yeah, we have been through a very good amounts of problems to solve, a very good number of techniques to try to overcome all of them, but yeah, we're not satisfied yet. What could we do? What could we do next to bring this particular style, particular network, particular technology to produce even better and better reconstruction? In the first place, I think we can use some more innovative technologies like transformers or diffusion models that seems like to work very well in this particular context. I'm not sure yet about the speed. I don't think they are ready to be run in real time, but I think we're getting there. Then we should focus into make even smaller architectures and learn how to train them in some more efficient way. Because if you want to deal with videos, if you want to restore videos, we have to do it in real time. And the only way to do it is shrink as much as possible those architecture. And the last problem that I'm telling you right now is about blind restoration. That is a very huge problem. Let's say you have a video, an old video that is distorted, is corrupted by some source of corruption. You don't know what, you don't know how, and you want to bring back to high quality life. Yeah, at the moment this is not possible because you will need a network that is trained to learn about all kind of distortion, all kind of parameter that have effect on distortion. It's too much. Basically, it's too much. So, if you want to do this, you have to understand how the distortion process has happened. You have to get some knowledge about these distortions, how the distortion have modified our image, and we are not there. Maybe for faces, someone has done blind face reconstruction. It works very well, but because as before, if you use a very small distribution, very narrow distribution, you could do very whatever you want. But in general, if you want to do blind restoration on of generic purpose, you simply cannot do it. You have to think about some way to tackle this problem and make it work. Okay, this is it for this presentation. I hope you enjoyed it, and if you have some questions, I'll be happy to answer.